Welcome to Introductory Chemistry with Dr. H. This is an introduction to quantum theory. I'm going to talk today about the particle-wave duality of light, and then I'm going to talk about the photoelectric effect a little bit more specifically, and then we're going to talk about Bohr and the quantization of energy level in atoms. This is a topic that we're going to expand as the course goes on. This is just the introduction. So first we're going to talk about the fact that we can think about light as having two different types of properties. One type of properties are the wave-like properties. And when we think about a wave, what we think about is something that's oscillating in time and in space. And so light propagates through space. It has some wavelength associated with it. It has an amplitude or intensity, and that it moves through space. Importantly, light is a kind of wave that is known as electromagnetic radiation, because rather than just having one component, it has two components that move orthogonally to each other, perpendicular to each other. It has an electric field component, which oscillates, and at the same frequency, but in a perpendicular axis, it has a magnetic field that oscillates. So that's the reason why we call this light, electromagnetic radiation. One thing about light that's very wave-like is that its speed, what we call c, is equal to the wavelength of that light, lambda, times its frequency, nu. So c equals lambda nu. And that speed of light is constant in a vacuum. It is, with a little bit of rounding, 3.00 times 10 to the 8th meters per second with 3 significant digits. So that speed of light is fixed, and so if we know the speed of light and either the frequency or the wavelength of that light, we can calculate the variable that we don't know. We can also relate that wavelength of light to the energy of the light. So energy of light is equal to h, which is called Planck's constant, 6.63 times 10 to the minus 34 joule seconds, times the frequency, or written in another way using the equation above, hc over lambda. The Planck's constant times the speed of light divided by the wavelength. Both of those will give us the energy of that light in joules. So electromagnetic radiation, as you're probably already familiar, can come in quite a wide range of wavelengths. Only a small set of those wavelengths are visible to our eyes. But things like X-rays are higher in energy. They can move right through our tissues. Things like radio waves are much lower in energy, and they surround us all the time, but they don't interact with our bodies at all. So the wavelengths of light which are visible range from the blues at around 400 nanometers. A nanometer is 10 to the minus 9th meters. So 400 times 10 to the minus 9th meters of light is in the blue. Greens are around 500. Orange is around 600. And the reds are around 700. And we call things even longer than that the infrared light. So in any case, this is just a little bit about the wave-like properties of light and how it falls on this spectrum of light. Now let's talk a little bit about the particle nature of light. So light has a particle nature as well, and the way this was discovered was something called the photoelectron effect, and Einstein sort of postulated that this is what was happening. And we think about the particle of light as a photon, or a small packet of energy that is the smallest quantum of light that you can imagine, a photon. And the way this was discovered was Einstein noticed or predicted that we require a certain frequency of photon in order to eject an electron from a piece of metal. So the observation was if you shine light, even a lot of it, with a frequency that is too low in energy, electrons won't be ejected, even if you shine a very, very bright light on the surface of a piece of metal. But as soon as you increase the energy, or increase the frequency, or decrease the wavelength of that light enough, and one particle of that light has enough energy, an electron will be ejected. And so what that means is it requires an individual packet of light that contains enough energy to eject an electron. That's called the photoelectric effect. And so, waves don't behave that way. Waves would say if we just put enough wave energy into the metal, we would start ejecting electrons by increasing the intensity. But we can't do it just by increasing the intensity of the light or the number of photons hitting. We have to increase the frequency. And so that sort of lends itself to a model where light has a particle-like aspect. And so we think about waves as having both this wave and the particle-like aspect. Some of the things still hold. So the energy of one photon, thinking about it as a particle, is this thing, Planck's constant times the frequency, or if you want hc over lambda, that's the energy of one packet, one photon of light. So Einstein formalized this and did a bunch of experiments to show that this photoelectric effect, this thing about ejecting electrons from metals, was real. And this is the equation that resulted. The energy of light, or h times nu, Planck's constant times the frequency, equals the kinetic energy of the ejected electrons plus some work function. This work function is the amount of energy that's required to get the electron just out of the surface. And so if the light has enough energy that's equivalent to or greater than that work function, the electron will be ejected. And any additional energy that that photon of light has will be represented in the kinetic energy of that electron, so the movement of that electron out of the metal. So if you were to shine a light on a metal that had exactly the energy of the work function, that electron would pop out, but then it wouldn't go anywhere. It wouldn't have any kinetic energy. But if you increased the frequency, the energy, or decreased the wavelength, right? Decreasing the wavelength means increasing the energy. By this equation right here, if we decrease the wavelength, the energy goes up because the wavelength is in the denominator, then we would see those electrons being ejected having some amount of kinetic energy. So the work function is this word for the minimum amount of energy to eject a photon, or to eject an electron from a metal. So it's the minimum amount of energy in a photon to eject an electron, and any additional energy would be going to the kinetic energy of the ejected photon. Okay, so this is the particle wave duality. Let's do a little bit of work with the photoelectric effect and see kind of how it can be applied. You can look up on tables to find the work functions of lots of different metals. So as it turns out, titanium metal has a work function of 6.93 times 10 to the minus 19 joules. What's the longest wavelength of light that is capable of ejecting an electron from the surface of titanium? Okay, so let's just use this equation. We know that h nu is the same as the energy of the photon, which is the same as hc over lambda. We're asked about the wavelength, so I figured we need an equation with lambda. And this, by this equation for the photoelectric effect, is going to be equal to the kinetic energy of the ejected electrons plus that work function. If we're just getting just enough energy to eject that electron, that electron from the surface of the metal, that electron would have no kinetic energy. So we're asking for the minimum amount of energy to eject, but then not give any kinetic energy. So this is going to be 0 if we're at the bare minimum energy. So now we have a pretty simple equation to work with. We've got hc over lambda equals that work function. And so if we're interested in the lambda, we can solve this for lambda. That's going to be hc over the work function, and let's just go ahead and plug some numbers in. Here's the Planck's constant, 6.63 times 10 to the minus 34 joule seconds, times the speed of light in a vacuum, which is 3.00 times 10 to the 8th meters per second. And we're going to divide that by the work function in titanium, which is 6.93 times 10 to the minus 19th joules. And what you'll notice is joules units cancel, seconds cancel, and we're going to be left over with meters. And so what I see when I punch this into my calculator is 2.87 times 10 to the minus 7 meters. And so usually we talk about wavelengths in terms of nanometers when we're talking about light. So what we would do is we would multiply that number by 10 to the ninth, because there are 10 to the ninth nanometers per meter, and we would see we have light of 287 nanometers. That would be the longest wavelength of light that is capable of ejecting electrons from the surface of titanium. Okay, so that was kind of A. Let's just read B. Would blue light with a wavelength of 465 nanometers be capable of ejecting an electron? Well, based on question A, we know that 287 nanometer light is the longest wavelength of light that would work. So the answer is no, it wouldn't be. So we wouldn't eject any electrons. You could shine as many photons of blue light as you want, but none of those photons have enough energy to eject any electrons, even if you're just flooding the surface with light. So there we go. Okay, so it looks like there's a third part to this question. What would the kinetic energy of an ejected electron be if a photon with a frequency of 1.0 times 10 to the 17th per second was shined on it? Okay. So let's go ahead and do that example. I'm going to kind of erase this, and we'll start with this last part. So again, we're going to use this equation. E equals h nu equals the kinetic energy of the ejected electrons plus the work function, right? And now what we're after is we're after this kinetic energy. So let's go ahead and solve this equation for the leftover kinetic energy. So I would have, it's not lambda, it should be h nu. Let's correct that, h nu. So h nu minus the work function equals the leftover kinetic energy. And let's just plug some numbers in here. So we have 6.63 times 10 to the minus 34, 34, let me make that clear, 34 joule seconds, times this frequency, which is 1.00 times 10 to the 17th per second. And we're going to subtract from it the work function, which is given in the question, 6.93 times 10 to the minus 19th joules. And notice the units again. The seconds part of this first term cancel with the seconds there, and we're left with joules, as we must. So when I plug this into my calculator, let's see what we get. We get 6.56 times 10 to the minus 17th joules equals the kinetic energy of an electron that is ejected by that frequency of light. Okay, so there we are. We expect a pretty small energy because we're talking about the energy of a tiny, tiny particle that's ejected. So that's a pretty small energy, and so it makes sense. Good. So next, what I want to talk about is I want to talk about the quantization of energy levels in atoms. And one thing that gave rise to this, this theory was that when you take an element and you put it in a discharge tube where you're applying a high voltage across that element that's in a tube, what you see is, rather than just like a glow of light with all different wavelengths, is you see very specific wavelengths of light. So if that light that is emitted from that discharge tube is split by a prism, you actually see very specific colors, if you will, of light, or wavelengths of light if it's outside of the visible spectrum, that are emitted. And the Bohr is the first one that came up with this idea that there are only certain energy levels allowed for electrons within atoms. And so one way we can imagine that happening is, let's say, we're just going to take a really physical look at this. If we had, say, an electron that was down here at the lowest possible energy level, and you put a bunch of energy in the form of that high voltage, and you excited it up to this energy level up here. So that step is a quantized step of energy uphill in energy. And then if you allow that electron then to relax back down, it has lots of different options. It can jump down one energy level, and that difference in energy from this higher energy level to that lower energy level, that energy has to be released in some way, and it's going to be released in terms of a photon. That photon there, that would be a really small energy gap. Maybe it has a red color because that's the difference in energy, because the smaller the energy, the longer the wavelength, and red light is the longest energy light here that's indicated in this particular example. Perhaps you excite an electron to this energy level and it jumps all the way down to the ground level. That's a much bigger energy difference, so you would get, say, a violet wavelength of light. This energy difference would be equal to a much bigger gap. So again, E, or in this case, the change in energy levels, equals h nu, the wavelength of light that's emitted. And this model obviously is not exactly the way the interior of an atom looks, but the idea is good. The idea is valid. Maybe electrons can only exist in certain energy states, quantized energy levels, and they can only move between them. And when we see light either going into an atom or being emitted from an atom, that light has to correspond with some gap between two different energy levels. And there's no rule that an electron has to go down only one energy level. Maybe it can go down 2, or maybe it can go down 3 energy levels. And the further it goes, the bigger that energy gap, the higher the frequency of light that comes out, or the shorter the wavelength. Okay, so there we go. And so this, as it turns out, works really well for the hydrogen atom. And Bohr and a number of other scientists figured out exactly what energy levels were involved in transitions for all different kinds of electromagnetic radiation for hydrogen. So you'll notice that this table right here is for atomic hydrogen emission spectrum, right? So this is only the energy levels in hydrogen. Different elements are going to have different energy spacings. But for example, Lyman noticed that if the final energy state of the electron is 1, this ground state, you can relax from an energy level state of 2, from 3, from 4, and each one of those is going to correspond to a bigger energy difference, right? A more high energy of light. As it turns out, the Lyman series is too high energy for us to see. That is ultraviolet light, high energy light. Balmer is the one who discovered the transitions for visible light. So here we're talking about transitions where the state that the electron is landing in is the second energy level in the hydrogen atom. And it's coming from 3, from 4, from 5. Those energies of light lead to visible colors that we can see. And there are other series like the Passion and Bracket series that are much shorter wavelengths than we can see, or longer wavelengths that we can see. Those are too small of an energy for the creation of visible light. So there's this equation that allows us to relate what energy level the electron's transitioning from and to, and the color of the light, the frequency of the light, or the wavelength of light. And this is it right here. Before I go into that, let's start using a little bit more specific terminology. This n number for the energy level is called the principal quantum number. Okay, and so we talk about electrons transitioning between levels with different principal quantum numbers. So if we're talking about the Balmer series of emissions, we're always talking about something coming from a principal quantum number of 3 or 4 or 5 and transitioning down to the level with quantum number 2. So all of these transitions right there. If we want to know the energy of any of those transitions, here's the equation that helps us. It's the Rydberg constant, 2.18 times 10 to the minus 18th joules, times this difference that involves the principal quantum numbers. And if the principal quantum number where the electron ends up is greater than the principal quantum number that the electron started in, the initial principal quantum number, that means that a photon has been absorbed. So what we're talking about is not this process of the electron falling down. We're talking about a principal quantum number that's higher in the final state, meaning a photon of light has been absorbed to promote an electron from a lower energy level to a higher energy level. So this table sort of makes it look like you can only emit electrons, but really you can also absorb photons in order to excite electrons in this system just as well. And of course, if the initial state is a greater principal quantum number than the final state, we're talking about an emission. Here we're talking about a process that looks like this, where an electron starts in the principal quantum number 3, say, and goes down to the 2 and generates some red light. Okay, so this is the quantization of energy levels in atoms, and this is the way we understand hydrogen-like atoms. So let's do a quick example just to make sure that this is totally clear. So what wavelength of light would be emitted from a hydrogen atom with an electron transitioning between n equals 4 to n equals 2? So we're starting at a higher principal quantum number energy level and going down to a lower principal quantum number. So we're talking about an emission. That's already stated there in the problem. So let's use this equation. And we want a wavelength. So delta E equals h nu, which equals hc over lambda. And so I use that form of the energy of the light because I know I wanted to get to wavelength. That's going to equal the Rydberg constant, RH, which value is right there. And in this case, the initial level is 4, so it's going to be 1/16 because the initial level squared would be 16 minus 1 over 1/4. And so now it's just a matter of sort of plugging and chugging a little bit. So if I do that math, what I find is, let's see, I guess let's just go ahead and solve this equation for the wavelength. So I'm gonna stop right there with that equals, and I'm just gonna say the wavelength is gonna equal hc divided by this whole term down here. You can do it either way, but okay. And so when I calculate that wavelength, I just plug in the numbers for the speed of light in the vacuum, for Planck's constant, the Rydberg constant, and that difference. What I find is the wavelength of light is 4.875 times 10 to the minus 7 meters. And so we really only have 3 sig figs on all of these constants, so that's going to be 488, and put a dot there to make Alex happy, nanometers. So that's the wavelength of light. So this is also a blue color of light. So that's the color of light that would be emitted from an n equals 4, principal quantum number of 4 to principal quantum number of 2 emission in a hydrogen-like atom. Okay, so this is the first discussion of quantization or quantum mechanics for understanding the electronic structure in atoms. And I hope you found it useful. We'll be talking more about this as we go.